Hey guys, I'm William and welcome back to the channel. In this video, I'll be going over the solutions to the November edition of the California Math League. Alright, last time, please note that you can pause the video to look at each problem before I go over the solutions, or alternatively, use the link posted in the description to glance at them. Without further ado, let's begin the work. Here's problem 1. The product of the non-zero digits of 2022 is the cube of an integer. What's the greatest integer less than 2022 whose product of its non-zero digit is also the cube of an integer? Since the problem asks for the greatest integer less than 2022 that checks the given requirements, we can just work backwards to solve the problem. It turns out that 2014 is the solution as 2 times 1 times 4 equals 8. The takeaway is that when we have maximum problems, we have to do a casework in which you have to find the maximum, prove that it works, and nothing above can work. Second is problem number 2. One end of a 5-meter pole is 3 meters from the base of a wall on which the pole leans. For what integer n greater than 0 would a pole move n meters further from the wall base when the pole slips n meters down the wall? The 5-meter long ladder is given to touch the ground 3 meters away from the wall space, and using the Pythagorean theorem, the wall is going to be touched at the height of 4 meters. The problem asks us to find the integer n such that if the ladder touches the ground at 3 plus n meters away from the wall's base, it's going to contact the wall at a height of 4 minus n meters. By the Pythagorean theorem, once again, 3 plus n squared plus 4 minus n squared is 225, and that simplifies to 2n times n minus 1 equals 0. N has to be positive, so n equals 1. This problem is one of the easier problems, so all we had to do was understand what the problem was asking, set it up, and solve it. A harder challenge is problem 3. Of the 100 fractions whose numerators are integers from 1 to 10 and whose denominators are also integers from 1 to 10, what percent are already in lowest terms? We can break down the problem. We can realize that the lowest terms means it can't be simplified. The numerator and denominator have a greatest common divisor of 1. We have 100 fractions to check, with the numerator and denominator both integers in the range from 1 to 10. The thing is, the GCD function of 2 variables is really unpredictable, but we can save time in our casework by setting either the numerator to equal 1 and then 2, and then you just keep going. We should also look at the prime factorization of the two numbers in the fraction to make sure we're doing this correctly. Let's do this as an example. If the numerator is 1, all fractions are in lowest terms. If the top is 2, we need to have an odd denominator. For 3, can't be divisible by 3. Get the point? We can just keep going until we get 63. So how to get a feel for this problem? If we can split this into multiple categories or outcomes, we need to use casework. It may be tedious, but for something as unpredictable as the GCD, it may do the job. We can also find a trick that can save time, just like how we did by setting the numerator fixed, and that may save time that we can use to solve the remaining competition problems. Let's go on to number 4. Each vertex of a square is connected to one of the trisection points of a side of the square, not containing that vertex as shown. The area of the square is 360, so what is the area of the shaded region? It looks like the shaded parts are rhombus. There are many methods to solve this question, but I'm going to use coordinate geometry, a method that's also taught in geometry class. And it may be inelegant at times, but it can make geometry problems simple in the right situation. And this is one of the situations where I feel like it's appropriate. So let's label the points 0, 0, 0A, A0, and AA, where A is greater than 0. The area of the square is A squared, and that's equal to 360. Recall that the top and the bottom sides were trisected, and the corners are connected to the trisections as such in the figure below. We need to find the points of trisections and the equation of the lines that connect the trisection and corners. Next, we have to find the intersection points of those lines. And then we can use the area of the rhombus formula, which is equal to half the product of the diagonals. We can just measure the length of the diagonals by using the distance formula or vice versa or something else. And once we do this, we get the area to equal 30. As in geometry problems, like in October, we can just draw new lines or use coordinates to find lengths, angles, and areas that we need to solve the problem. Now comes problem number 5. What are all ordered pairs of integers xy for which 2xy minus 7 equals 5x cubed? How on earth does the CAML expect contestants to be able to solve an equation like this? This is really unfair, isn't it? But let's focus. This is an equation. The problem doesn't want us to just solve for one variable in terms of the other. We have to solve in integers, but maybe if we solve, we can force restrictions. Shall we? Notice that there isn't a neat way to express x in terms of y because the cubic formula has to come to play. But we can solve y in terms of x. And when we do this, we get 2y equals 5x squared plus 7 over x. Yes, this is not y, but for the sake of convenience, I'll explain why I put it in this form. 2y is an integer, right? 5x squared is also an integer. So therefore, 7 over x has to be an integer, but x is an integer, and so integer times integer has to equal 7. And 7 is prime, so we can easily find the prime factorization as 1 times 7 or 7 times 1, but we also have to consider the negatives. But even then, it's just a flip up sign, so it's minus 1 times minus 7 or minus 7 times minus 1. There are only 4 pairs of x times, let's call it the integer n, 4 pairs such that equals 7 when we do consider the order in which the numbers are multiplied. Therefore, we have 4 values of x that are possible, and as a result, 4 values of y are also possible. And once we figured out that x can only equal 1, 7, minus 1, or minus 7, we can just plug that into the original equation and solve for y. And we get 4 solutions. My final words for this problem is that we're getting a Diophantine equation, which is generally nearly impossible for high school students who don't know much of number theory. So I'll explain some ways to approach these equations. We can reduce the equation modulo something, we can go small, or we can convert the equation into a much neater form for solving, as we did in this solution. But stop. Problem 5 was not the hardest. If you think so, let's talk about number 6. A sequence consisted of only ones, only zeros, or both zeros and ones. Any zero in the sequence must be one of an odd number of consecutive zeros. Any one in the sequence must be one of an odd numbers of consecutive ones. How many such different 10-term sequences are possible? You can make an argument that this was the hardest question from any CAML contest in 2022-2023. Even I panicked to the point that I almost couldn't solve the problem. How is it that the last 2 problems are so hard that it was nearly impossible to score in this section? But let's not panic. Let's make our count easier, and let's consider what the sequence has to be. What it's saying is that each string of zeros and ones has to be of odd length. Also, if the sequence starts with ones, we can just interchange the ones and zeros. That way, we create a valid sequence partner because the number of terms is 10. The length of each string of zeros and one, they're still odd. But note that the new sequence we created starts with 0. Therefore, we can make the assumption that the sequence starts with 0, but we have to multiply whatever we get by 2 to get the true solution. So let's consider the case when the sequence is of length 1. And just note that we want the sequence to start with 0. Length 1, there's one sequence. Length 2, there's also one sequence. Length 3 has 2. Length 4 has 3. The pattern isn't clear yet, but if we test length 5, we would have obtained 5. It seems like we have 1, 1, 2, 3, 5. And if you know, this might be familiar to you. This is like the Fibonacci sequence, isn't it? But why is it true? Or why is it this way? We need to define more terms here so we can see whether this is true or not. Let's denote z of n to be the number of sequences of length n that start with 0, and t of n to be the number of sequences of length n that start with 1. As observed before, z of n is equal to t of n. So our goal is to prove that the Fibonacci rule applies. That means we have to form the next term by adding the previous 2 terms. So z of n plus 2 should equal z of n plus 1 plus z of n. Normally, recurrences like these can be proven with construction. So this refers to the way the solver constructs a configuration that satisfies the given conditions. By definitions, any sequence of z of n plus 2 has to start with 0. But there are 2 cases for the second number. Case 1, the second number is 0. But by the odd string rule, since we have 2 zeros, we need to make sure we have to add a third 0. But how can we proceed? The key is to realize that we remove the first two zeros we're constructing. We get a valid sequence of length n. But why? The sequence initially starts with an odd string of zeros that measure 3 terms or more. But since any odd number minus 2, which is an even number, is still odd, we can truncate the sequence and we still have an odd string of zeros. It can now be of length 1, but the point is, we get a valid sequence of length n. And to get the original sequence, we can just add the 2 zeros back, can't we? This example is a great illustration of a bijection. It's a pairing that pairs each element of a set to an element of a different set. These sets have to be of the same size. There are no leftover elements, and each element can only be paired once. We just found a way to match each distinct member of the set of sequence with length n plus 2 that starts with 0, 0, with a distinct member of the set of sequences with length n that starts with 0. And since we found a way to do this, the number of elements in most sets must be equal. But by definition, the size of the second set has to equal z of n. So therefore, in case 1, we just counted z of n sequences. How about when the second number is 1? There's no constraint for what the third number of the sequence can be, but note that we can just remove the 0. The bijection rule is we can cut off the 0 at the start to obtain an okay sequence of length n, because it starts with 1. But know that we can change back to 0. But that was exactly the point in which I was defining t of n. So basically, we can truncate the 0 and we get a sequence that starts with 1. It's length n plus 1, and there's no restriction. So the number here is t of n plus 1, but by observation, that was equal to z of n plus 1. We can add the two cases together to finally prove that z of n plus 2 has to be the sum of the previous two terms. Let's put up all of this together. We know that z of 1 was equal to 1, z of 2 equals 1, and da-da-da. We can just keep going with the Fibonacci sequence until we get z of 10 equals 55. But the count was twice this, so we have to multiply by 2, and so the solution is 110. This is without question the hardest question of this CAML. Sequences like 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, and 0, 0, 1, 1, 0, 0, 1, 1, 0 fail to satisfy the condition of the problem. So how are we going to count the number of possible sequences? The best way is to start off with a few terms of a sequence, because the odd string rule makes counting extremely complicated. A pattern can emerge, but we have to use intuition and think that the pattern may emerge. We can use intuition and think that the pattern goes to 110. If you can't prove that the pattern always holds, we shouldn't just waste time because we may get lucky here. But if you don't believe in naive guessing, it's still okay. In combinatorics problems, a good strategy is to consider how we count the number of goods and analyze their construction. Do this only if you can see the insight that immediately breaks the problem open easily. I say a tip is to think about bijections. As I explained in the solution for problem 6, it's a powerful tool that eases the counting of satisfactory configurations. This method works by relating each member of one set to a distinct member of a different set, and you can't have leftover or repeated elements. So it's like 1 match 1 something. If it's too hard to count something, then we can find a relation and point the fact that two sets in any bijection must be of the same size or count. So make sure to find a relation that makes your counting easier to perform. I suggest you can look up casework generating functions, or you can just keep practicing combinatoric problems in the Olympiads/math competition so that you can gain more insight and develop your skills so that whenever you tackle a problem like this, you're more prepared and you may be getting points here. And that's the end of this video. I really hope that I helped you guys go through the solutions of the problems of this CAML math contest. If you know how to solve all the problems, that's great. But otherwise, I'm so glad that you can use this to improve your skills. Thanks for listening, and I'll see you next time.